Hello everyone, welcome to Sleep Space. Tonight we will talk about everything you've ever wondered about Tellurian planets. Get comfortable, settle in, and let your mind relax as we take a deep and gentle dive into the science of rocky worlds. The kinds of planets we could one day walk on, build on, or perhaps even call home. Tellurian planets, also known as terrestrial or rocky planets, are solid Earth-like worlds. Unlike the gas giants of our solar system, these planets have firm surfaces and are composed mainly of rock and metal. Earth is a prime example, along with our neighbours, Mercury, Venus, and Mars. Each one is unique, yet they share key characteristics that place them in this category. They are small compared to the gas giants, but incredibly dense. They're born from dust and fire, shaped by collisions and carved by weather, gravity, and time. To understand where Tellurian planets come from, we have to travel back, far back, to the birth of solar systems themselves. Imagine a swirling cloud of gas and dust in the depths of space, rich with the building blocks of everything: hydrogen, helium, silicates, iron, and ice. Over millions of years, gravity begins to pull this cloud inward. The densest regions collapse and start to spin, forming a flat disk around a growing protostar. This disk is called a protoplanetary disk. It's hot near the center, where the star forms, and cooler as you move farther out. That temperature gradient plays a huge role in which types of planets can form in different regions. Near the center, it's too hot for ice or volatile gases to condense, but metals and silicates, the ingredients for rocky planets, can survive the heat. So it's here, in this inner part of the disk, that Tellurian planets take shape. Tiny grains of dust begin sticking together. These clumps become larger, forming planetesimals, objects several kilometers across. Through a chaotic and violent process of accretion, planetesimals collide, merge, and grow, forming embryonic planets called protoplanets. Some of these grow large enough to clear out their orbits and become full-fledged planets. The ones that remain rocky and dense, usually closer to their star, are the Tellurian planets. Let's return to our own solar system as a guide. Mercury, the closest planet to the Sun, is a small, heavily cratered world. It's made mostly of iron, with a very thin silicate crust. It has virtually no atmosphere because its gravity is too weak to hold on to gases in the face of intense solar radiation. Next is Venus, similar in size and structure to Earth, but shrouded in a thick, toxic atmosphere rich in carbon dioxide, with clouds of sulfuric acid. Its surface pressure is more than 90 times that of Earth, and temperatures soar above 460 degrees Celsius, hot enough to melt lead. Then there's Earth, the only known Tellurian planet to host life. Its surface is dynamic and alive, with plate tectonics, oceans, a breathable atmosphere, and a magnetic field that shields us from solar radiation. Finally, Mars, cold, dry, and dusty. But it wasn't always that way. Evidence suggests that Mars once had flowing water, a thicker atmosphere, and possibly even conditions suitable for life. These four planets form the rocky inner core of our solar system, orbiting within the frost line, the region where it's too warm for volatile ices to condense. Beyond the frost line lie the gas giants, Jupiter, Saturn, Uranus, and Neptune. Massive planets composed mostly of hydrogen, helium, and ices. But our focus tonight remains on the inner planets, the ones made of rock, forged in fire. What exactly are Tellurian planets made of? They're composed mainly of silicate rocks, the same kind found in Earth's crust. and metals like iron and nickel, especially in their cores. Many have layered internal structures, a crust, a mantle, and a core. The crust is the outermost layer, made of solid rock. The mantle lies beneath it, often composed of silicate minerals rich in magnesium and iron. The core, usually made of metal, can be solid, liquid, or a combination of both. This internal structure plays a crucial role in a planet's geology and magnetic field. For instance, Earth's molten outer core generates a magnetic field through a process called the geodynamo. The movement of liquid iron creates electric currents, which in turn produce a protective magnetic field. This shield deflects harmful solar particles and preserves our atmosphere. Mars, on the other hand, lost its magnetic field billions of years ago, and with it, much of its atmosphere. That's one reason Mars is now dry and frozen, instead of warm and wet like it might have been in the past. A planet's surface features also tell stories of its history. Impact craters are universal. Lava flows indicate volcanic activity. Canyons and riverbeds speak of erosion and water, even when no liquid remains. Earth, with its plate tectonics, has reshaped its surface countless times. Mars, without plate tectonics, preserves ancient terrains. Venus has a young surface, possibly due to periodic global resurfacing events caused by massive volcanic activity. Mercury, scarred by billions of years of impacts, shows us what a geologically quiet world looks like. The atmospheres of Tellurian planets vary wildly. Earth's is rich in nitrogen and oxygen, supporting life and regulating temperature. Venus's atmosphere is thick with carbon dioxide, trapping heat through an intense greenhouse effect. Mars has a thin, mostly carbon dioxide atmosphere, unable to maintain surface warmth. Mercury, being so small and close to the Sun, has only an exosphere, a tenuous layer of atoms blasted off its surface by solar radiation. Despite their differences, all Tellurian planets share something remarkable. They are solid ground in a universe of gas, ice, and plasma. They are the most Earth-like worlds we know, and they offer the most promising locations in the search for life beyond our planet. As astronomers look beyond our solar system, they've discovered thousands of exoplanets, planets orbiting other stars. Many of these are believed to be rocky, and some are located in the so-called habitable zone, where conditions might allow for liquid water. These discoveries fuel our hope that Earth is not unique, that Tellurian planets are common in the galaxy, and perhaps even in the universe. But how do we study these distant worlds? How do we know what they're made of, or what their atmospheres are like from light years away? The answers lie in powerful telescopes, careful measurements, and clever techniques like transit photometry and spectroscopy. When a planet passes in front of its star, it blocks a tiny bit of light. By studying that dimming, we can infer the planet's size, orbit, and sometimes even its atmosphere's composition. It's like reading the ingredients of a planet by looking at the way light changes as it filters through. Our understanding of Tellurian planets, both in our solar system and beyond, is expanding rapidly. Missions like NASA's Kepler and TESS, and upcoming projects like the James Webb Space Telescope, are pushing the boundaries of what we know. With each discovery, we move closer to understanding how common Earth-like planets truly are, and whether life could exist elsewhere. So tonight, as you drift into rest, imagine walking across the rugged surface of Mars, feeling the low gravity tug at your feet. Picture the glow of a sunrise on a rocky world orbiting a distant star. Envision a future where humanity reaches out to these worlds, not just to explore, but perhaps to live. The universe is vast, but Tellurian planets are the islands of solid matter in that cosmic sea, and we are just beginning to chart them. When we talk about Tellurian planets, we're often drawn to their surfaces, the mountains, valleys, volcanoes, and canyons. But much of their identity lies deeper, hidden beneath layers of rock and metal. The internal structure of a rocky planet reveals clues about its formation, history, and even its potential for life. Tonight, we'll journey inward, through crust, mantle, and core, to uncover what lies beneath the surface of these fascinating worlds. Let's begin with the crust. On Earth, the crust is the outermost shell, thin compared to the planet's total size, yet vital. It's where we live, build, and explore. Earth's crust varies in thickness, thinner beneath oceans and thicker beneath continents. It's made of silicate minerals like quartz, feldspar, and mica. Other rocky planets also have crusts, though they differ in composition and history. Mars has a crust rich in basalt, a volcanic rock. Venus has a basaltic crust as well, but its intense heat and pressure make its surface incredibly harsh. Mercury's crust is heavily cratered and ancient, showing little sign of renewal. Beneath the crust lies the mantle, a thick layer of silicate rock under high pressure. Earth's mantle is partially solid, but behaves plastically over time, allowing convection currents to form. These slow-moving currents drive plate tectonics, causing continents to drift, mountains to rise, and earthquakes to occur. The mantle transfers heat from the core toward the surface, a process that shapes much of a planet's surface activity. Mars has a mantle, but without active plate tectonics. It shows evidence of past volcanic activity, including Olympus Mons, the tallest volcano in the solar system. This suggests Mars once had mantle convection, but that activity has since slowed or ceased. Then comes the core. Earth's core is composed of iron and nickel and is divided into two parts: a solid inner core and a liquid outer core. The movement of molten metal in the outer core generates Earth's magnetic field. This magnetic field extends into space, forming the magnetosphere, an invisible shield that protects life from harmful solar radiation and cosmic rays. Other Tellurian planets also have cores, but their states vary. Mercury has an unusually large core for its size, suggesting it may have lost much of its mantle in a massive collision early in its history. Surprisingly, despite its small size, Mercury has a magnetic field, weak but present, hinting that its core may still be partially molten. Venus, nearly Earth's twin in size and mass, lacks a global magnetic field, leading scientists to wonder whether its core is fully solid or not convecting. Mars once had a magnetic field, but it faded long ago. Without a protective magnetosphere, Mars's atmosphere was gradually stripped away by solar wind. Understanding the magnetic fields of Tellurian planets is more than a technical curiosity. It's deeply tied to a planet's ability to support life. A magnetic field preserves a planet's atmosphere, shields against harmful radiation, and may even stabilize climate. That's why the loss of Mars' magnetic field had such devastating consequences, transforming what may have been a wetter, warmer world into the dry, frozen desert we see today. But what determines whether a rocky planet has a magnetic field? Its delicate balance of factors: a liquid, convecting metallic core, sufficient planetary rotation, and internal heat. Earth ticks all the boxes. Venus, despite its similar size, rotates extremely slowly. One day on Venus lasts longer than its year, which may contribute to its lack of a magnetic field. Mars, though it rotates quickly, may have cooled too much, stalling convection in its core. Now let's turn our attention to the surface processes that shape Tellurian planets. On Earth, tectonics play a major role. Plates of the crust float atop the mantle and shift slowly over time. These shifts create mountains, cause earthquakes, and recycle the crust through subduction zones. This continuous activity is unique among the known Tellurian planets. Venus shows evidence of surface deformation, but it doesn't appear to have active plate tectonics. Instead, its surface may periodically undergo massive volcanic resurfacing events, where lava floods over large areas, erasing older features. Mars, while geologically inactive today, once had massive volcanoes and long canyons carved by ancient water. Its surface tells a story of a world that cooled and quieted over time. Olympus Mons, the solar system's tallest volcano, is a testament to that ancient activity. Because Mars lacks plate tectonics, its volcanoes could grow much larger, erupting in place for millions of years without being shifted by moving crust. Mercury, the smallest of the four, has a surface marked primarily by impacts and contraction. As its interior cooled, Mercury shrank slightly, causing the surface to wrinkle and crack, forming long scarps and cliffs that stretch for hundreds of kilometers. This process, called planetary contraction, is unique in its scale on Mercury and provides insight into how planets evolve as they lose internal heat. Volcanism is another common thread among Tellurian planets. All four show evidence of past or present volcanic activity. On Earth, active volcanoes continuously reshape the surface and enrich the atmosphere. Venus has volcanic plains and possible signs of recent eruptions, although thick clouds obscure direct observation. Mars had extensive volcanism in the past, and some lava flows appear geologically young. Mercury's smooth plains suggest ancient volcanic resurfacing as well. Let's also talk about erosion, the gradual wearing away of surface features by wind, water, or ice. On Earth, erosion is constant and dynamic. Rivers carve valleys, glaciers sculpt mountains, and winds shape deserts. Mars once had rivers and possibly even lakes or oceans, and its dried-up channels still mark the terrain. Wind-driven dust storms continue to reshape its surface today. Venus, with its dense atmosphere, experiences minimal erosion, and Mercury, lacking an atmosphere, is shaped mainly by impacts and space weathering. Impact cratering is perhaps the most universal process affecting all Tellurian planets. The solar system was a chaotic place in its early days, and collisions were frequent. Craters serve as time capsules, preserving a record of these ancient impacts. Earth's active geology erases many craters over time, but others, like the Chicxulub crater, linked to the extinction of the dinosaurs, remain. Mars, Mercury, and the Moon, which is technically not a planet but shares characteristics with Tellurian worlds, have surfaces densely marked with impact sites. The study of craters also tells us about surface ages. A heavily cratered surface is old. A smooth, crater-free region is young and recently resurfaced. This method of planetary dating is crucial for understanding the geological history of these worlds, especially those we cannot visit directly. Now, let's pause for a moment and imagine what it would feel like to stand on each of these rocky worlds. On Mercury, you'd experience intense sunlight and freezing shadows, as its lack of atmosphere means temperatures swing dramatically from day to night. You'd weigh just 38% of your Earth weight and hear nothing, Sound doesn't travel well without air. On Venus, you'd be crushed by atmospheric pressure nearly 100 times that of Earth's and cooked in temperatures hot enough to melt metal. The sky would be an eerie yellow-orange, filtered through thick clouds of sulfuric acid. Your spacecraft would need to survive both extreme heat and a corrosive atmosphere. On Mars, you'd feel a gentle tug. Gravity there is about 38% of Earth's, and see a pink sky above rust-colored deserts. The air would be thin and unbreathable, and you'd need a pressurized suit to survive. But unlike Venus or Mercury, the Martian landscape would feel strangely Earth-like. Mountains, canyons, and the remnants of rivers long gone. These imagined landscapes aren't just fantasy. They're based on decades of data from orbiters, landers, and rovers sent to explore our rocky neighbors. Each mission adds pieces to the puzzle, helping us refine our understanding of Tellurian planets. NASA's Magellan mapped Venus's surface using radar. The Messenger spacecraft revealed Mercury's interior structure. Rovers like Curiosity and Perseverance trundle across Mars, analyzing rocks and searching for signs of ancient life. The deeper we go into the science of Tellurian planets, the more they reveal about themselves, about our own planet, and about the conditions that make life possible. They're not just scientific curiosities. They are keys to understanding our place in the cosmos. The story of Tellurian planets doesn't stop at our solar system. In recent decades, astronomers have looked beyond, discovering rocky planets orbiting distant stars, exoplanets that resemble Earth, Mars, and Venus in mass and size. This cosmic expansion of our understanding has reshaped our idea of what's possible. We once thought Earth might be unique, a rare jewel in an empty sky. But now we know, rocky worlds are everywhere. Let's start with the basics. What exactly qualifies a planet as Tellurian outside our solar system? The same core characteristics apply: a solid surface, a composition rich in silicates and metals, and a relatively small size compared to gas giants. These planets are generally less than 1.5 to 2 times the radius of Earth and under 10 times its mass. Beyond this threshold, a planet is likely to accumulate a thick envelope of hydrogen and helium, making it more like a mini Neptune than a super Earth. One of the biggest breakthroughs in exoplanet science came with the launch of NASA's Kepler Space Telescope. Kepler stared at a small patch of sky for years, monitoring the brightness of over 150,000 stars. When a planet passed in front of its star, an event called a transit, the light dipped slightly. By analyzing these dips, astronomers could calculate the size and orbit of the planets causing them. Thousands of exoplanets were discovered this way, and a significant portion turned out to be Tellurian or close to it. Many were in the so-called habitable zone, the region around a star where temperatures might allow liquid water to exist on the surface. But habitability is more complex than just temperature. A planet needs an atmosphere, the right pressure, internal heat, a magnetic field, and ideally, geologic activity. In short, it needs to be more than a rock at the right distance. Some of the most intriguing discoveries include Proxima Centauri b, orbiting the closest star to our own. It's slightly more massive than Earth and lies within its star's habitable zone. Then there's the TRAPPIST-1 system, a compact planetary system 40 light-years away with 7 rocky planets, at least 3 of which might be capable of holding liquid water. These worlds are tightly packed, orbiting a small, cool red dwarf star, and their arrangement suggests a stable configuration that could last for billions of years. But how do scientists determine what these exoplanets are made of? It begins with transit data, which reveals a planet's size. When paired with radial velocity measurements, subtle shifts in the star's spectrum due to the gravitational tug of orbiting planets, astronomers can calculate a planet's mass. With mass and radius, we can determine density. A dense planet is likely rocky. A lower density suggests gas or a thick, volatile atmosphere. This method doesn't give a detailed composition, but it helps categorize planets into types: rocky, icy, gaseous. Some exoplanets are super-Earths, larger than Earth, but still likely to have solid surfaces. Others are sub-Neptunes, planets smaller than Neptune, but with thick atmospheres and potentially no solid surface at all. As observational techniques advance, we're beginning to study the atmospheres of rocky exoplanets as well. Instruments like the James Webb Space Telescope, JWST, can analyze starlight passing through a planet's atmosphere during a transit. Certain molecules, water vapor, carbon dioxide, methane, leave chemical fingerprints in the spectrum. If we ever detect a mix of gases that suggest biological activity, such as oxygen alongside methane, it could be the first clue that life exists elsewhere. But even without life, these planets tell us about planet formation. For example, we've learned that rocky planets often form early in a star's life. Their composition is influenced by the materials in the protoplanetary disk and the energy of collisions. Some may begin as rocky and later accumulate gas, while others may lose their atmospheres over time due to stellar winds or flares. The diversity is astounding. Some rocky exoplanets orbit so close to their stars that they're tidally locked. One side always faces the star, bathed in perpetual daylight, while the other side remains in endless night. Temperatures may swing by hundreds of degrees from one hemisphere to the other. Others orbit small, dim red dwarfs, where flares and radiation may strip away atmospheres unless magnetic fields offer protection. It's worth noting that our solar system lacks certain types of planets that are common elsewhere. Super-Earths, for instance, don't exist here, but they are among the most frequently observed types in other systems. This raises questions about why our solar system developed the way it did. Did early migrations of giant planets disrupt the formation of intermediate mass rocky worlds? Did Earth narrowly escape becoming a gas-rich planet? These are mysteries planetary scientists are still trying to unravel, and each new rocky exoplanet adds a piece to the puzzle. Let's now turn our gaze back to the formation process itself, a chaotic, violent dance that gives birth to rocky worlds. In the early stages of a star's life, gravity gathers dust and gas into a rotating disk. Within this disk, dust particles collide and stick, gradually forming larger and larger bodies. These become planetesimals, then protoplanets, and eventually planets. But the journey is brutal. Protoplanets collide, often violently, exchanging material or breaking apart entirely. Earth's moon likely formed from such a collision, a Mars-sized body impacting the young Earth, ejecting debris that coalesced into our satellite. Similar events probably shaped Mercury's large iron core, stripping away much of its mantle in a cataclysmic impact. In this sense, every Tellurian planet carries scars from its birth: craters, layers, tilted axes, and even moons. Mars has two small moons, Phobos and Deimos, that may be captured asteroids. Earth has one large, stable moon that helps stabilize our axial tilt and tides, potentially aiding the development of life. Venus rotates in the opposite direction of most planets, possibly the result of a major collision. Its slow spin and lack of a large moon make it a strange outlier. Each of these characteristics holds clues to the violent history of rocky planet formation. And then there's the matter of planetary systems themselves. Our solar system is neatly organized, with small rocky planets close to the Sun and gas giants farther out. But in other systems, this isn't always the case. Some have gas giants in close orbits, hot Jupiters, likely formed farther out and migrated inward. This migration can disrupt the orbits of smaller planets, scatter them, or even eject them from the system entirely. In systems where rocky planets survive, their placement often depends on the stability of their orbits and the gravitational influence of neighboring worlds. Some rocky planets are caught in orbital resonances, repeating patterns that help keep their position stable. Others may be in multi-planet systems, where gravitational interactions cause complex dynamics. Despite this complexity, the emergence of rocky planets seems to be a common outcome. The raw materials, silicates, metals, ices, are abundant in the galaxy. Gravity pulls them together, energy sculpts them, and time matures them. Rocky planets may not be rare, they may be the rule. This realization reframes our understanding of the universe. For centuries, Earth seemed unique, a solitary outpost in the void. Now, we understand that there are likely billions of rocky planets in the Milky Way alone, and possibly trillions across the universe. Each of these worlds has its own history. Some are scorched and barren, others frozen and silent. A few might be temperate, with oceans and clouds and climates not so different from our own. And somewhere, perhaps, life has taken hold, not just microbes, but ecosystems, maybe even civilizations. But for now, we observe from afar, reading the light of distant stars for signs of rocky companions. We study their gravity, their orbits, and their shadows. We build models of their interiors and imagine what their skies might look like. And in doing so, we deepen our understanding not just of those distant worlds, but of Earth, our own Tellurian home, in all its fragile, beautiful complexity. As we continue our exploration of Tellurian planets, it's time to take a closer look at one of the most intriguing aspects of rocky worlds: habitability. The question of whether a planet can support life, or even host it right now, has driven science, philosophy, and imagination for centuries. But in the context of planetary science, habitability isn't about hopes and dreams. It's about measurable conditions. What makes a rocky planet truly habitable? Let's begin with the basics. To support life as we know it, a planet needs a few key ingredients: liquid water, a stable climate, a protective atmosphere, and a source of energy. The presence of water is perhaps the most critical factor, and so scientists often look for planets located in a star's habitable zone. The range of distances where surface temperatures could allow water to exist in liquid form. However, the concept of a habitable zone is far more complex than simply being the right distance from a star. It depends on the star's temperature, the planet's atmosphere, its reflectivity and internal heat. Earth sits comfortably in the Sun's habitable zone, but Venus is slightly closer to the Sun and suffers from a runaway greenhouse effect, making it uninhabitable. Mars, on the other hand, is slightly farther out, cold and dry today, but it may once have supported liquid water. The greenhouse effect plays a major role in shaping planetary climate. On Earth, gases like carbon dioxide and water vapor trap heat and keep the surface warm. Without it, our planet would be a frozen ball of ice, but too much greenhouse gas, as seen on Venus, leads to extreme temperatures and atmospheric pressure. Finding the right balance is essential. Atmospheres are also crucial in regulating temperature, recycling materials, and protecting against harmful radiation. Earth's atmosphere, rich in nitrogen and oxygen, supports complex ecosystems. Mars's atmosphere is thin, composed mostly of carbon dioxide, and offers little protection. Venus has a thick atmosphere, but it's toxic and crushing. The presence of an atmosphere isn't enough. Its composition, pressure, and thickness all matter. Another critical factor is planetary mass. A Tellurian planet needs enough gravity to retain an atmosphere and possibly sustain geological activity. If a planet is too small, like Mars, it cools quickly and its atmosphere escapes. If it's too large, it might begin to accumulate hydrogen and helium, transitioning into a gas giant or sub-Neptune. Internal heat is vital too. It drives plate tectonics, volcanism, and magnetic fields. Without it, a planet may become geologically dead. Earth's molten core creates a magnetic field that shields us from solar wind. Mars, having lost its magnetic field, gradually lost its atmosphere as well. Magnetic fields act like invisible umbrellas, deflecting charged particles that could otherwise erode the atmosphere and irradiate the surface. Another question arises: must a planet have plate tectonics to be habitable? On Earth, tectonics help regulate carbon dioxide through the carbon-silicate cycle. Volcanic eruptions release CO2 into the atmosphere, while weathering of rocks pulls it back down into the crust. This natural thermostat helps maintain a stable climate over geological time. We don't know if other rocky planets have similar systems, but their absence could mean a planet's climate is far more vulnerable to change. Now let's talk about water. On Earth, it covers over 70% of the surface, exists in solid, liquid, and vapor forms, and cycles through the atmosphere and crust in a complex balance. It dissolves minerals, supports life, and helps regulate temperature. Water is so essential that we use it as a marker for potential habitability elsewhere. Mars provides a compelling case study. Evidence suggests it once had rivers, lakes, and maybe even oceans. Ancient river valleys, lake beds, and sedimentary rocks are visible from orbit. Polar ice caps remain, and water ice exists beneath the surface. Recent observations suggest that salty, briny water may even occasionally flow near the surface today. But without a thick atmosphere or magnetic field, liquid water can't remain stable on Mars for long. It quickly evaporates or freezes. Venus, meanwhile, may have had oceans billions of years ago, but intense solar radiation combined with volcanic outgassing and a thickening atmosphere triggered a runaway greenhouse effect. Water was likely lost to space, stripped away as hydrogen and oxygen by solar wind. The result is the hostile, superheated world we see today. In the search for life, scientists are also exploring the idea of extended habitability. Could a planet orbiting outside the traditional habitable zone still support life under the right conditions? For example, a planet with a thick hydrogen atmosphere could trap enough heat to maintain liquid water even far from its star. Or a planet with intense geothermal activity could have underground oceans like the moons Europa or Enceladus, which aren't planets, but show us what's possible. Then there are tidally locked planets, common around red dwarf stars. These planets always show the same face to their star, with one side in permanent daylight and the other in eternal night. For a long time, scientists thought this would make them uninhabitable, with one side scorched and the other frozen. But more recent models suggest that a thick atmosphere or ocean currents could distribute heat effectively, creating habitable zones along the terminator, the line between night and day. But habitability isn't just about physical conditions. It's about stability over time. A planet needs to maintain those conditions for billions of years to allow life to arise and evolve. That means having a stable orbit, minimal interference from nearby giant planets, and a host star that isn't too volatile. Red dwarfs, for instance, are small and long-lived, good for longevity, but often emit powerful flares that could strip atmospheres from nearby planets. Let's also consider biosignatures, the chemical fingerprints of life. On Earth, life alters the atmosphere in measurable ways. Oxygen is a byproduct of photosynthesis and would not exist in large amounts without biological input. Methane, carbon dioxide, and even certain ratios of nitrogen to oxygen can also hint at life. Detecting these gases in the atmosphere of an exoplanet could be the first step toward discovering extraterrestrial biology. The upcoming generation of space telescopes, like the JWST, and future missions like LUVOIR and HABEX, aim to study these biosignatures. By analyzing light from distant stars as it filters through a planet's atmosphere, scientists can detect specific molecules. This technique, called transmission spectroscopy, has already been used to study the atmospheres of gas giants, and is now being refined to detect smaller, rocky worlds. But we must remain cautious. Abiotic processes, those not related to life, can also produce oxygen or methane under certain conditions. A volcanic planet, for example, might emit methane without any biological activity. To confirm life, we may need multiple biosignatures appearing together in the right ratios, or even seasonal changes in atmospheric chemistry, a sign of ongoing biological processes. Some scientists also explore the concept of technosignatures, evidence of intelligent life. This could include artificial light, unusual chemical pollutants, or even alien radio signals. While this area of research is speculative, it adds another layer to the search for habitability. The possibility that other civilizations might have altered their environments in detectable ways. Habitability isn't binary, it's a spectrum. A planet might be marginally habitable, with only microbial life in extreme environments. Another could be a paradise teeming with oceans, forests, and animals. Still others might hover on the edge, habitable for a time, then lost to climate change or stellar activity. Earth itself has swung between ice ages and hot houses, survived asteroid impacts and mass extinctions, and yet has remained habitable for over 4 billion years. That resilience is part of what makes Earth so special, but it also makes us realize how delicate the balance is. A small shift in orbit, a drop in magnetic field, or an increase in greenhouse gases can transform a habitable planet into a lifeless rock. Studying other Tellurian planets helps us understand those tipping points, not just in theory, but as real possibilities. As we search the galaxy for other Earth-like worlds, we carry with us a deeper understanding of what makes a planet livable, and how rare that perfect combination might be. The more we learn, the more precious Earth becomes. Yet, the search continues, because even if most rocky planets are barren, lifeless stones, it only takes one distant, living world to prove that life can take hold beyond Earth. And maybe, someday, we'll find it. As we have explored the formation, composition, and habitability of Tellurian planets, it becomes clear that their diversity is vast, even within the same category. These rocky worlds can differ dramatically in temperature, pressure, chemistry, and geological activity. To understand them fully, we must also study the dynamic processes that continue to shape their surfaces and interiors over time. Let's begin with one of the most transformative forces on any rocky planet: volcanism. Volcanic activity is more than just dramatic eruptions. It's a deep expression of a planet's internal heat, a process that connects the interior to the surface. On Earth, volcanoes are part of a broader system that includes plate tectonics and the movement of the mantle. They recycle materials, release gases into the atmosphere, and even contribute to climate cycles. On other Tellurian planets, volcanism takes different forms. Mars, for instance, has some of the largest volcanoes in the solar system. Olympus Mons stands over 21 kilometers tall, nearly 3 times the height of Mount Everest, and spans a base wider than the state of Arizona. Unlike Earth's volcanoes, which erupt in isolated regions due to plate boundaries, Martian volcanoes may have formed over stationary hotspots without the shifting of crustal plates to distribute the activity. This allowed single volcanoes to grow immensely over millions of years. Venus also shows signs of extensive volcanism. Its surface is covered in volcanic plains, lava flows, and possibly active volcanic vents. Although we haven't directly observed an eruption, thermal imaging and atmospheric chemistry suggest the planet may still be volcanically active today. Without plate tectonics, Venus may instead experience episodic resurfacing, periods where vast amounts of lava erase old terrain in relatively short geological bursts. Mercury, on the other hand, is less volcanically active now, but shows signs of past eruptions. Smooth plains indicate lava once flowed across the surface, filling low-lying areas and covering impact craters. These flows likely occurred early in the planet's history, fueled by residual heat from formation and radioactive decay. Even the Moon, Earth's companion, and a Tellurian body in its own right, experienced ancient volcanic activity. The dark regions we call Maria are vast basaltic plains formed by ancient lava eruptions. Though now geologically quiet, the Moon preserves this early record in stunning detail. Another surface process common to rocky planets is tectonic activity, though Earth remains the only known planet with active plate tectonics. The shifting of large crustal plates is a major driver of surface renewal and mountain building. Earth's tectonic boundaries give rise to ocean trenches, mountain ranges like the Himalayas, and seismic activity. These processes constantly reshape the planet's crust. On Mars, there's no evidence for Earth-like tectonic plates, but there are massive rift valleys, such as Valles Marineris, a canyon system over 4,000 kilometers long and up to 7 kilometers deep. It's thought to have formed through crustal stretching and faulting, possibly related to the weight and stress of nearby volcanic provinces. Venus shows extensive surface fracturing and fault zones, indicating some form of crustal movement, though not in the segmented plate style we see on Earth. Mercury displays long ridges and scarps that suggest global contraction. As the planet cooled, it shrank slightly, causing its crust to buckle and fold. This form of tectonism is unique among the inner planets and offers insight into how planetary interiors evolve as they lose heat. Speaking of heat, let's explore thermal evolution, how rocky planets change as they cool over billions of years. Early in a planet's life, leftover heat from formation and heat from radioactive decay drive vigorous internal activity. Magma circulates, volcanoes erupt, and tectonic processes may reshape the surface. Over time, as a planet loses heat, this activity slows or stops altogether. Smaller planets cool faster, That's why Mercury and the Moon became geologically dead relatively early, while Earth, being larger, retains enough internal heat for active geology. Mars falls somewhere in between, once active, but now mostly dormant. Venus, similar in size to Earth, may still retain enough heat for sporadic volcanism, but lacks the plate tectonics that make Earth's surface so dynamic. This process affects not only the planet's surface, but also its magnetic field. As we discussed earlier, magnetic fields are generated by the movement of molten metal in a planet's core. When a planet cools and its core solidifies, that movement slows, and the magnetic field weakens or vanishes. This happened to Mars and possibly to Venus. Without magnetic shielding, solar wind strips away lighter atmospheric elements, altering the climate and reducing the planet's habitability. Let's turn now to erosion and weathering, which slowly wear down and reshape the surface features of rocky planets. On Earth, erosion is primarily driven by water, wind, and ice. Rivers carve valleys, glaciers scour landscapes, and wind smooths and transports sediment. These forces gradually recycle the surface, contributing to the planet's dynamic character. Mars also experiences erosion, but primarily through wind. Its thin atmosphere allows dust storms to sweep across the planet, reshaping dunes and covering ancient features with layers of fine sediment. Evidence suggests that water once flowed across Mars, and those ancient processes carved riverbeds and deposited sediments, clear signs of a more active hydrologic past. Venus, despite its thick atmosphere, experiences little erosion in the traditional sense. There's no liquid water, and winds near the surface are relatively slow due to the planet's dense atmosphere. However, the extreme temperature and pressure may chemically weather rocks in unusual ways. Its atmosphere, filled with sulfur compounds, likely interacts with surface minerals in a corrosive cycle we don't yet fully understand. Mercury, with no atmosphere to speak of, lacks erosion altogether. Its surface features remain largely unchanged over billions of years, except for the effects of micrometeorite impacts and solar radiation. This preservation makes Mercury a kind of time capsule, offering a window into the early history of rocky planets. Impact cratering, as discussed earlier, is another universal process. Every Tellurian planet has been struck by asteroids and comets. These impacts leave craters, some of which are massive. The more active a planet is geologically, the more it erases these scars over time. Earth, with its plate tectonics and erosion, has few ancient craters. Mars and Mercury, geologically quieter, display a much older and heavily cratered surface. These impacts don't just shape the landscape, they can also alter a planet's evolution. Large impacts can generate enough heat to cause localized melting, disrupt climate, or even create moons, as with Earth's own lunar-forming collision. Some impacts may have delivered water and organic materials, potentially seeding the early Earth with the ingredients for life. The final surface process we'll examine is regolith formation. Regolith is a layer of loose, fragmented material that covers solid rock. On Earth, it includes soil and sediment. On the Moon and Mercury, it consists of broken rock and dust from billions of years of impacts. Regolith plays an important role in planetary science. It affects surface temperature, reflects light, and can complicate or assist with landing spacecraft. Understanding all of these dynamic processes, volcanism, tectonism, erosion, impact cratering, and regolith development, helps scientists reconstruct the geological history of rocky planets. It tells us not just what they are now, but what they once were, and what they might become. Each Tellurian planet is like a layered book, with each chapter written in lava flows, craters, mountain ranges, and valleys. By reading these features with care, we piece together a story that spans billions of years. A story of heat, pressure, collisions, and time. And as we compare these stories across different worlds, we find both familiar patterns and surprising deviations. Earth is no longer alone in its complexity. The more we explore, the more we recognize the universality of rocky planet evolution, shaped by the same forces, but ending in wildly different outcomes. These differences help us define the boundaries of possibility. They show us not just what a planet must have to be habitable, but also what it can endure and still remain viable. In that, rocky planets are not just distant objects of study, they are mirrors reflecting back the nature of our own planet in cosmic context. In our journey through the world of Tellurian planets, we've looked deep into their geology, atmospheres, and potential for life. Now it's time to explore something equally fundamental: the chemical composition of rocky planets. From the iron in their cores to the silicates in their crusts, the elements that make up a Tellurian planet tell us where it came from, and hint at what might be possible on its surface. All Tellurian planets are composed primarily of refractory elements, those that condense at high temperatures and are abundant in the inner regions of solar systems. These include silicon, magnesium, iron, oxygen, aluminum, and calcium. These materials form rocks and metals, the fundamental building blocks of terrestrial planets. At the heart of most rocky planets lies a metal-rich core, usually dominated by iron and nickel. Iron, in particular, plays a critical role in the structure and magnetic properties of a planet. Earth's core is about 85% iron and 10% nickel, with trace amounts of lighter elements like sulfur or oxygen. The density and composition of the core affect everything from magnetic field generation to the amount of heat retained in the interior. Surrounding the core is the mantle, a thick, rocky layer composed mainly of silicate minerals. On Earth, the mantle includes minerals like olivine and pyroxene, which contain magnesium, iron, and silicon. These minerals can flow slowly under pressure, allowing heat to escape from the core and driving processes like convection and volcanism. Other planets have similar mantles, though differences in composition and temperature can lead to varying behaviors. Above the mantle lies the crust, the outermost shell of the planet. Crustal composition varies significantly across different Tellurian planets. Earth's crust includes both continental and oceanic components. The former is rich in granite, a light-colored rock containing quartz and feldspar, while the latter is primarily basaltic, denser and darker. Venus and Mars also have basalt-rich crusts, suggesting extensive volcanic activity in their pasts. Mercury, by contrast, has a crust rich in magnesium silicates, with large expanses of plains likely formed by ancient lava flows. Let's talk more specifically about each planet's elemental makeup. Mercury is high in iron. Its massive core makes up about 85% of the planet's radius. Scientists believe this may be the result of a giant impact early in its history that stripped away much of the lighter silicate mantle and crust. The surface is low in iron oxide, but shows high levels of sulfur, which is unusual for a rocky planet so close to the Sun. This hints that Mercury may have formed under chemically reducing conditions, very different from Earth. Venus has a composition similar to Earth's, with a silicate mantle and iron core, but its surface is heavily weathered by the planet's extreme atmosphere. The thick, CO2-rich atmosphere and sulfuric acid clouds chemically interact with surface minerals, possibly producing unique compounds not found on Earth. Remote sensing suggests volcanic basalts dominate the surface, indicating that Venus once had, and may still have, active geology. Earth, our baseline for comparison, is chemically complex. Its crust includes a wide range of minerals, including carbonates, sulfides, silicates, and oxides. The presence of liquid water and life has introduced additional processes, such as biomineralization and sedimentary layering, which further diversify Earth's chemistry. Our atmosphere, rich in nitrogen and oxygen, also plays a role in chemical reactions on the surface. Mars, meanwhile, is coated in iron-rich dust, giving it its reddish hue. The Martian crust is primarily basaltic, with high concentrations of iron, magnesium, and silicon. Volcanic rocks on Mars often contain olivine and pyroxene, similar to Earth's mantle. Evidence of hydrated minerals, such as clays and sulfates, suggests water once altered the surface chemistry. These hydrated minerals are key indicators in the search for past life. Even the Moon, though not a planet, is useful for comparison. Its composition is similar to Earth's mantle, with basaltic plains formed from ancient lava flows and highland regions rich in plagioclase feldspar. The Moon lacks volatiles, water, carbon, and other easily evaporated compounds, due to its low gravity and the violent conditions of its formation. Now, let's consider trace elements and volatiles, small components that can have outsized effects on planetary behavior. Elements like sulfur, carbon, hydrogen, and chlorine are present in low concentrations but are vital for atmosphere formation, volcanic gas chemistry, and even biological potential. Water, composed of hydrogen and oxygen, is a volatile compound that can exist in multiple forms across a Tellurian planet. On Earth, it's everywhere. On Mars, it's found in polar ice caps, buried beneath the surface, and possibly in briny flows. Venus likely had water early in its history, but intense heat and solar wind stripped it away. Mercury has water ice in permanently shadowed craters near its poles, a surprising discovery for a planet so close to the Sun. Carbon is another key element. On Earth, it's essential to life, forming the backbone of organic molecules. Carbon also exists in the crust as carbonates, in the mantle as carbon-bearing minerals, and in the atmosphere as carbon dioxide. Mars and Venus also have significant carbon dioxide in their atmospheres, though for different reasons. Venus's thick carbon dioxide atmosphere drives a runaway greenhouse effect, while Mars's thin atmosphere fails to trap heat effectively. Sulfur is abundant on Venus, likely from volcanic outgassing. It forms sulfuric acid clouds that reflect sunlight and contribute to the planet's harsh climate. On Earth, sulfur is found in minerals and emitted by volcanoes. On Mars, sulfates provide clues about ancient water activity. Chlorine, while less glamorous, is important for understanding soil chemistry. On Mars, perchlorates, chlorine-based salts, have been found in the soil. These compounds can affect water stability and even microbial survival, making them a critical focus in the search for life. The presence and ratios of these elements can reveal a planet's formation environment. Planets that form closer to their star tend to have fewer volatiles due to high temperatures driving off lighter compounds. Those that form farther out may accumulate more ices and light elements. Migration, the movement of planets inward or outward after formation, can blur this distinction, but the general trend remains. Let's also consider planetary differentiation, the process by which a planet separates into layers of differing composition: core, mantle, and crust. This process occurs early, when the planet is still molten. Denser materials like iron sink to the center, while lighter silicates float toward the surface. Differentiation is critical in determining the planet's internal structure and long-term evolution. Not all rocky bodies differentiate fully. Some small asteroids and dwarf planets are undifferentiated, remaining chemically mixed throughout. These objects offer a window into the early solar system, preserving the building blocks of rocky planets. Studying meteorites, many of which are fragments of these primitive bodies, helps us understand the raw materials from which Tellurian planets formed. Now, let's zoom out and look at stellar composition. A star's chemical makeup can influence the types of planets that form around it. Stars rich in heavy elements, often called metal-rich stars in astronomy, are more likely to host rocky planets. This is because metals, in astronomical terms, include all elements heavier than helium and are essential for forming solid planetesimals. If a star is poor in heavy elements, its protoplanetary disk may not have enough solid material to form large rocky planets. Observations of exoplanet systems confirm this trend. Stars with higher metallicity tend to have more Earth-sized or super-Earth planets. Some stars even show chemical signatures that match the composition of known planets. For example, if a star is deficient in refractory elements like aluminum and calcium, it might suggest those elements were sequestered into rocky planets during formation. This kind of stellar fingerprinting is a growing field, helping astronomers infer the presence and nature of planets that are too distant or faint to detect directly. All of this brings us to a deeper understanding. The chemical story of a Tellurian planet is not static. It evolves. Volcanism changes surface composition. Impacts deliver new materials. Atmospheric escape alters gas ratios. Water, when present, transforms rocks and enables complex geochemistry. And if life emerges, it can transform the planet completely, introducing oxygen, organics, and new cycles. Earth's own chemistry is inseparable from its biology. The oxygen in our atmosphere is a product of photosynthesis. The carbon cycle is driven by plants, animals, oceans, and geology. If life exists elsewhere, we may recognize it not by its appearance, but by the chemical signatures it leaves behind. In rocks, in gases, in the subtle changes it etches into a world over time. So when we study the chemistry of rocky planets, we're not just studying minerals and metals. We're looking for signs of activity, of transformation. We're looking for clues that the planet is not merely a rock in space, but a system, a story, maybe even a home. Throughout our exploration of Tellurian planets, we've studied their origins, structures, dynamics, chemistry, and potential for life. But to fully appreciate the significance of these rocky worlds, we must place them within their broader cosmic context, not just where they are, but how they interact with the systems around them. This part of the story focuses on planetary systems, how Tellurian planets exist and evolve alongside other celestial bodies, and what that tells us about the nature of rocky planets as a whole. Let's begin by looking at planetary architecture, the arrangement of planets within a star system. Our own solar system provides a familiar model: 4 small rocky planets close to the Sun, followed by 4 giant planets farther out, with a scattered region of icy bodies beyond. This layout suggests that rocky planets form closer to their star, where temperatures are higher and volatile materials are less likely to condense. But this arrangement isn't universal. Observations of other planetary systems reveal an astonishing variety of configurations. Some systems contain multiple Earth-sized planets packed closely together, orbiting well within the distance from the Earth to the Sun. Others have gas giants skimming the surfaces of their stars, hot Jupiters, while rocky planets are completely absent or pushed to the fringes. A prime example is the TRAPPIST-1 system, located about 40 light-years from Earth. This red dwarf star is surrounded by 7 Earth-sized planets, most of which orbit closer to their star than Mercury does to the Sun. And yet, because the star is much cooler and dimmer, several of these planets fall within the habitable zone. Their densities suggest rocky compositions, making TRAPPIST-1 one of the most promising systems for studying the diversity of Tellurian planets. Why are such compact systems possible? The answer lies in disk evolution and migration. When planets form, they don't always stay in the same location. Interactions with the gas and dust of the protoplanetary disk can cause them to move inward or outward. Some rocky planets may be born farther from their star, only to migrate closer over time. Others may be formed near the star but get pushed aside by the gravitational pull of larger neighbors. This brings us to planetary migration, a process that can drastically reshape a system's layout. Jupiter, for instance, may have migrated inward in the early solar system before reversing course. Its movement could have influenced the formation of the inner planets, possibly scattering or destroying early rocky worlds and limiting the size of Mars. In other systems, such migrations can disrupt or stabilize the orbits of rocky planets, affecting their potential for long-term habitability. The presence of giant planets can be both a blessing and a curse for Tellurian planets. On one hand, they can act as cosmic shields, sweeping up comets and asteroids that might otherwise impact inner planets. On the other hand, they can destabilize orbits, ejecting rocky planets or causing destructive collisions. In some systems, giant planets migrate so close to their stars that they prevent rocky planets from forming at all. Let's consider the role of moons in planetary systems. Earth's large moon plays a stabilizing role by moderating our planet's axial tilt. This helps maintain a relatively stable climate over long time scales, a potential factor in Earth's ability to support complex life. In contrast, Mars's small moons, Phobos and Deimos, offer little stabilizing influence, and its axis wobbles more dramatically. A large moon may not be essential for habitability, but it can help create a more stable environment. Exomoons, moons orbiting planets in other star systems, have yet to be confirmed, but are actively being searched for. If found, they could be habitable in their own right, especially if orbiting gas giants within a star's habitable zone. These moons could possess rocky surfaces, atmospheres, and even internal heating from tidal forces, making them Tellurian bodies in their own unique niche. Now let's look at asteroids, comets, and impacts. These small bodies play a big role in the story of Tellurian planets. In the early stages of planetary formation, impacts from asteroids and comets helped deliver water and organic materials. On Earth, some scientists believe that much of our surface water came from icy bodies that collided with the planet during the late heavy bombardment, a period of intense impacts roughly 4 billion years ago. Impacts can also be destructive. The Chicxulub impact, which struck Earth 66 million years ago, caused a mass extinction that ended the age of the dinosaurs. Other large impacts have reshaped planets, created moons, and even altered planetary spin and orbit. For Tellurian planets, the balance of impacts, their timing, frequency, and scale, plays a critical role in shaping habitability. Asteroid belts, such as the one between Mars and Jupiter, represent leftover material that never coalesced into a planet. In some star systems, these belts are much more massive, leading to frequent collisions that may disrupt any nearby rocky planets. In others, the belts are sparse, and rocky planets evolve in relative peace. Let's also talk about resonances and orbital dynamics. In tightly packed planetary systems, the gravitational influence of neighboring planets can create stable patterns of motion. These resonances, where orbital periods follow simple ratios, help prevent collisions and allow multiple planets to coexist in close proximity. The TRAPPIST-1 planets, for example, are locked in a complex web of resonances that maintain their alignment and spacing. In other cases, gravitational interactions lead to chaos. Eccentric orbits, close encounters, and even ejections from the system. Some rocky planets may end up as rogue planets, wandering interstellar space without a star. These lonely worlds could still retain internal heat, possibly even subsurface oceans beneath thick ice shells. Though cold and dark, they might offer niches for life under the right conditions. When we expand our view to binary star systems, the picture becomes even more complex. Many stars exist in pairs, orbiting each other. Rocky planets can still form in these systems, either orbiting one star in a wide loop, S-type orbit, or circling both stars together, P-type or circumbinary orbit. The gravitational forces are more chaotic, but stable orbits are still possible, and several such systems have been confirmed. These planets experience exotic day-night cycles and unusual climate patterns, depending on the configuration of their stars. Another dimension of planetary systems involves stellar evolution. Stars change over time, growing brighter and more energetic. A planet that begins its life in the habitable zone may one day find itself too hot as its star ages. In the far future, Earth itself will become uninhabitable due to the sun's increasing luminosity. Understanding this evolution helps us determine not just if a planet is habitable now, but how long it can remain so. Some Tellurian planets may have already passed through such transitions. Planets that were once warm and wet may have lost their atmospheres, frozen over, or become barren. Others may just be entering habitable conditions as their stars stabilize and cool. This temporal window for habitability is another key consideration as we survey exoplanets. In some systems, planets may form in extreme environments, close to high radiation stars, near black holes, or within dense star clusters. While life may seem unlikely in such places, rocky planets could still form and evolve. And in environments rich with stellar interactions, new materials and energy sources may appear. This widens our perspective of where Tellurian planets might thrive. Ultimately, the story of any Tellurian planet is shaped not just by what it is, but by where it is and what surrounds it. The dance of planets, moons, asteroids, stars, and gravitational forces creates a complex environment, one that can support, challenge, or destroy the delicate balance required for habitability. By studying these systems holistically, we come closer to answering the biggest questions. How common are Earth-like worlds? What kinds of planetary systems can support life over long timescales? Are we a cosmic rarity, or just one example among billions? The more we learn, the more we see that Tellurian planets are not isolated. They are members of intricate families, shaped by and shaping their stellar environments. They are players in vast cosmic systems, each one a different outcome of the same physical laws. And within these systems, amid the light and shadow, heat and cold, silence and collision, rocky planets persist. So far, we've explored the formation, composition, dynamics, and environments of Tellurian planets. But to truly appreciate their complexity, we must dive deeper into a field that bridges chemistry, physics, and biology, the study of planetary atmospheres. For rocky planets, the atmosphere is not just a blanket of gases, it's a dynamic system that governs weather, protects from radiation, drives surface erosion, and may even help sustain life. Let's start by asking a basic question. Where do atmospheres come from? For Tellurian planets, atmospheres are born from several sources. The first is primary accretion. When planets form, they may capture light gases like hydrogen and helium from the surrounding nebula. But because these gases are light and the gravity of small, rocky planets is weak, primary atmospheres are usually lost quickly, especially if the planet is close to a star. The second source is outgassing, where volcanic activity releases gases from the planet's interior. This is how Earth's early atmosphere formed, a mixture of water vapor, carbon dioxide, nitrogen, and sulfur compounds released from molten rock. Other planets, like Venus and Mars, followed similar paths, but their outcomes diverged. A third source is delivery by comets and asteroids, which bring volatiles like water, carbon, and nitrogen. These materials, added after the planet's formation, may have played a critical role in forming secondary atmospheres and surface oceans, especially in Earth's case. Once an atmosphere is in place, its fate depends on several factors: the planet's gravity, magnetic field, temperature, and distance from its star. These variables determine whether gases are retained or lost, how they circulate, and how they evolve over time. Let's look at the atmospheres of the 4 terrestrial planets in our solar system to understand this better. Mercury essentially has no atmosphere. Its tiny mass and proximity to the Sun make it unable to hold onto gas molecules. Instead, it has what scientists call an exosphere, a very thin, transient collection of atoms ejected from the surface by solar wind, radiation, and micrometeorite impacts. The exosphere contains small amounts of sodium, potassium, helium, and hydrogen, but it's not stable or protective. Venus has an incredibly thick and hostile atmosphere composed of about 96.5% carbon dioxide, with small amounts of nitrogen and traces of sulfur dioxide. Surface pressure is over 90 times that of Earth, and the temperature hovers around 465 degrees Celsius, hot enough to melt lead. The dense atmosphere traps heat via a runaway greenhouse effect, making Venus the hottest planet in the solar system, despite being farther from the Sun than Mercury. Venus's upper atmosphere also contains clouds of sulfuric acid, which reflect sunlight and contribute to its high albedo, brightness. These clouds, combined with a slow rotation and high-altitude winds, create a dynamic and alien weather system, including global superrotation, where winds travel much faster than the planet's surface. Earth has a unique and dynamic atmosphere, rich in nitrogen, about 78%, and oxygen, about 21%, with trace gases like carbon dioxide, water vapor, and argon. This composition is crucial for supporting life. Oxygen, a byproduct of photosynthesis, wouldn't exist in large quantities without life itself, making it a biosignature on other planets. Our atmosphere is divided into layers: troposphere, stratosphere, mesosphere, thermosphere, and exosphere, each with distinct characteristics. The ozone layer in the stratosphere protects life from harmful ultraviolet radiation. The carbon cycle balances CO2 levels, and weather systems distribute heat and water across the globe. The presence of liquid water, plate tectonics, and life makes Earth's atmosphere uniquely complex among known planets. Mars has a thin, cold atmosphere, mostly carbon dioxide, about 95%, with nitrogen and argon. The surface pressure is less than 1% of Earth's, and temperatures can swing dramatically from day to night. Without a magnetic field, solar wind gradually stripped Mars of its atmosphere, leaving it unable to retain surface water or maintain stable climate conditions. Despite its thin atmosphere, Mars experiences dust storms, sometimes covering the entire planet. There's also evidence of past climate change, including periods where the atmosphere may have been thicker and capable of supporting lakes, rivers, and possibly life. Now let's consider the key atmospheric processes that affect all Tellurian planets. Radiative balance, how energy from the star is absorbed, reflected, and re-emitted. Albedo, greenhouse gases, and atmospheric composition determine a planet's energy balance and surface temperature. Atmospheric escape, the loss of gas to space. There are multiple escape mechanisms. Thermal escape, light molecules reach escape velocity. Non-thermal escape, caused by chemical reactions or solar wind. And impact erosion, where collisions blow part of the atmosphere into space. Weather and circulation, how air moves around a planet, distributing heat, moisture, and energy. Factors like rotation speed, axial tilt, and topography influence wind patterns, cloud formation, and precipitation. Chemical cycles, including the carbon cycle, nitrogen cycle, and water cycle. These cycles regulate atmospheric composition over time and are often linked to geological and biological processes. In addition to these, atmospheres can also carry aerosols, tiny particles suspended in gas. On Earth, aerosols come from volcanic eruptions, forest fires, ocean spray, and human activity. They influence climate by reflecting or absorbing sunlight and can trigger cloud formation. Venus's sulfuric acid clouds and Mars's dust are natural aerosols that shape those planets' climates. Another atmospheric phenomenon to consider is photochemistry, the chemical reactions driven by sunlight. On Earth, photochemistry produces ozone and breaks down pollutants. On Mars and Venus, it drives the creation and destruction of trace gases. Detecting specific photochemical reactions on exoplanets could provide clues about atmospheric composition and potential life. Now let's move beyond our solar system. When studying exoplanet atmospheres, scientists use a method called transmission spectroscopy. When a planet passes in front of its star, some of the starlight filters through the atmosphere. By analyzing the spectrum of this light, scientists can identify the chemical fingerprints of gases, such as water vapor, carbon dioxide, methane, and oxygen. This technique has already revealed atmospheres on several exoplanets, particularly large gas giants. Detecting atmospheres on Earth-sized Tellurian planets is more difficult, but improving with each generation of telescopes. The James Webb Space Telescope, JWST, has already made significant advances, and future missions like the LUVOIR and HABEX concepts aim to study the atmospheres of potentially habitable rocky exoplanets in greater detail. These investigations raise a profound question. How many Earth-like atmospheres are out there? The diversity we see in our own solar system, from Mercury's near vacuum to Venus's inferno, from Mars's thin chill to Earth's life-filled air, suggests that rocky planets can support a wide range of atmospheric outcomes. The key is understanding the interplay of initial conditions, planetary mass, stellar radiation, magnetic protection, and internal processes. A planet's atmosphere is both a shield and a mirror. It protects life, if present, and reflects the processes happening below and above. It is shaped by the planet's interior, sculpted by its star, and, if life evolves, transformed by biology. And this makes atmospheric studies one of the most promising frontiers in the search for life beyond Earth. A planet with an oxygen-rich atmosphere, or with seasonal fluctuations in methane, or with unexpected chemical imbalances. These could all be signs of something more. Not every Tellurian planet will have an atmosphere. Many will be barren or toxic, but some, maybe just a few, will have the right balance of gases, the right pressures and temperatures, and perhaps even the faint breath of life stirring in the air. And for those worlds, we watch the light from their stars, passing through unseen winds, and we read their skies from across the void. In our quest to understand Tellurian planets, we've examined their structure, formation, environments, and atmospheres. But now we come to one of the most captivating and consequential aspects of rocky planets: the search for life. This part brings together biology, chemistry, astronomy, and geology to ask some of the most profound questions in science. What makes a planet truly habitable? How do we recognize signs of life elsewhere? And are we alone? Let's begin with the concept of habitability. At its core, a habitable planet is one that can support liquid water on its surface for extended periods. Water is the universal solvent for life as we know it. It allows chemical reactions to occur, transports nutrients, and helps regulate temperature. But water alone isn't enough. A habitable planet also needs a source of energy, a stable environment, and access to essential elements like carbon, nitrogen, hydrogen, phosphorus, and sulfur. These criteria define the habitable zone, often called the Goldilocks zone, the region around a star where temperatures are just right for liquid water to exist. For our Sun, this zone stretches roughly from the orbit of Venus to the orbit of Mars. Earth sits comfortably within it, but being in the zone isn't a guarantee of habitability. Venus is too hot, Mars is too cold, and both have lost most of their water. This brings us to the importance of planetary context. A planet's size, mass, and geological activity all play vital roles. A small planet may cool too quickly and lose its atmosphere. A planet without plate tectonics may lack a long-term carbon cycle. One without a magnetic field may have its atmosphere stripped away by solar wind. Habitability depends on a delicate interplay of many systems. One of the most exciting frontiers in planetary science is the search for biosignatures, detectable signs of life. On Earth, life has profoundly altered the atmosphere. Oxygen, for example, makes up about 21% of our air, but this is only possible because of photosynthetic organisms. Without life, oxygen would rapidly react with surface minerals and disappear. Other biosignatures include methane, nitrous oxide, and certain combinations of gases that would not coexist naturally. For instance, a planet with both methane and oxygen would be highly suspicious. These gases react with each other, so something must be constantly replenishing them. Life could be the explanation. Spectroscopy allows scientists to search for these gases in exoplanet atmospheres. The hope is that by examining the light that filters through or reflects off an atmosphere, we can identify signs of biological activity, even from light years away. But interpreting these signals is difficult. Some biosignature gases can also be produced by abiotic processes, that is, non-living chemistry. For example, ultraviolet light can break down carbon dioxide and water to create oxygen. Methane can be formed in hydrothermal systems or by impacts. So it's not just the presence of a gas that matters, but its context. How much is there? What else is present? Does the chemistry make sense? Scientists are also exploring surface biosignatures, such as specific patterns of light reflection, called spectral red edge, from vegetation, or pigments used by microbes. These would be far harder to detect than atmospheric signatures, but they represent another path to detecting life. Another intriguing avenue is technosignatures, signs of advanced civilizations. These could include artificial chemicals in an atmosphere, like chlorofluorocarbons, narrowband radio signals, or even artificial lighting on a planet's night side. While speculative, technosignature research broadens our perspective on what kinds of signs intelligent life might leave behind. Now let's consider alternative biochemistries. While carbon-based, water-dependent life is all we know, scientists speculate that life might arise using different solvents, like liquid methane or ammonia. Saturn's moon Titan, for example, has lakes of liquid methane and ethane, and complex organic chemistry in its atmosphere. While too cold for Earth-like life, it might support a completely different kind of biochemistry, one we wouldn't even recognize at first glance. Even among rocky planets, the conditions for habitability vary widely. Subsurface habitability is one such possibility. Planets or moons with thick ice layers might harbor liquid water oceans beneath, heated by tidal forces or radioactive decay. Jupiter's moon Europa and Saturn's moon Enceladus are prime candidates. They're not planets, but they show that rocky bodies, even in distant orbits, can maintain environments where life might emerge. Mars, too, may have subsurface water, salty, briny reservoirs protected from the harsh surface. If life ever existed on Mars, it might still persist below ground, shielded from radiation and climate extremes. One important point to remember is that life doesn't need to be complex. Most life on Earth throughout its history has been microbial. These simple organisms can live in extreme conditions, deep underground, in boiling hydrothermal vents, inside rocks, and in acidic, salty, or freezing environments. Earth's extremophiles provide models for how life might survive on other Tellurian planets with harsh climates. Searching for microbial life presents challenges. Even on Earth, we often need direct sampling and sensitive equipment to detect it. On another world, we may need rovers, landers, or drills to search for biosignatures hidden in soil or ice. Future missions to Mars, Europa, and Enceladus aim to do exactly that, to search directly for evidence of life, past or present. But what about detecting life beyond our solar system? For that, we rely on next-generation telescopes, tools designed to study the atmospheres of distant Tellurian exoplanets. Instruments like the James Webb Space Telescope, JWST, the Extremely Large Telescope, ELT, and proposed space missions such as LUVOIR and HABEX will be able to analyze starlight passing through planetary atmospheres in unprecedented detail. These observatories can detect temperature profiles, cloud layers, and gas compositions, all vital for assessing habitability. In the coming decades, we may detect Earth-like planets with water vapor, carbon dioxide, and perhaps oxygen, tantalizing signs that we are not alone. But even if we find no direct signs of life, the study of Tellurian planets will continue to reshape our understanding. Each rocky world is a laboratory, a place where physics, chemistry, and time have played out different experiments. By comparing them, we learn not only what is possible, but what is rare and what is universal. We also begin to see our own planet in a new light. Earth is not just a home, it is a member of a larger family of worlds. Its climate, its geology, and its biosphere are part of a continuum of planetary possibilities. Understanding Tellurian planets allows us to appreciate how fragile, dynamic, and precious our own world truly is. And it compels us to keep looking, to search the skies, to ask questions, and to remain open to wonder. Because somewhere, orbiting a distant star, there may be another rocky planet, bathed in starlight, with winds that stir across oceans, and perhaps even something breathing beneath its skies. Not every Tellurian world will be alive. Most will be silent stone, dust, and gas. But some may whisper back. Tonight we've taken a long journey, through stardust and stone, across time and space, to explore everything about Tellurian planets. As we bring this exploration to a close, let's reflect on what we've discovered and where it might lead us. Tellurian planets, rocky terrestrial worlds like Earth, Mars, Venus, and Mercury, are not just physical objects orbiting stars. They are dynamic systems forged in stellar furnaces, sculpted by gravity, chemistry, heat, and time. Their surfaces are written with stories of fire and water, of collisions and erosion, of silence and change. We began with their formation, learning how dust grains in protoplanetary disks clump together under gravity, growing into planetesimals, then into fully fledged rocky worlds. We saw how the position of a planet in its solar system, its distance from its star, shapes its destiny. Closer to the star, rocky materials dominate. Farther out, gas and ice take over. This is why Earth and Mars are solid, while Jupiter and Saturn are giants of hydrogen and helium. We explored the internal structures of these planets, with dense iron cores, convecting mantles, and diverse crusts. Each layer holds secrets of how planets cooled, how they spun, and whether they could protect their atmospheres with magnetic fields. These interiors drive volcanic eruptions, generate earthquakes, and even influence climate by recycling carbon through plate tectonics. We studied geology and surface processes, from ancient lava flows to tectonic shifts, from impact craters to icy regolith. Some planets, like Earth, remain geologically alive, their surfaces ever-changing. Others, like the Moon or Mercury, have fallen silent. Yet even those quiet worlds hold ancient stories, preserved for billions of years. Atmospheres added another layer of complexity. From Mercury's near vacuum to Venus's crushing greenhouse gases. From Mars's thin chill to Earth's breathable air. We saw how gases shape a planet's temperature, climate, and potential to support life. We learned how atmospheres evolve, escape, or become locked in feedback loops that can render a planet dead or alive. The chemical compositions of Tellurian planets revealed their diversity, rich in silicates, metals, and trace elements that hint at volcanic pasts, water-rich histories, or dramatic changes over time. We looked at how elements like iron, sulfur, carbon, and phosphorus cycle through planets, influencing geology and biology alike. We then broadened our view, examining planetary systems, how Tellurian planets interact with moons, asteroids, and other planets. We explored resonances and migrations, binary stars and rogue worlds, and saw that every planetary system is a unique arrangement of orbits, energy, and matter. Within these cosmic families, rocky planets can be nurtured, disrupted, or flung into the void. And then, the most compelling question of all, life. We asked what it means for a planet to be habitable, and how life could leave fingerprints on a planet's atmosphere or surface. We searched for biosignatures, imagined exotic chemistries, and considered the strange possibilities of life underground, under ice, or on moons orbiting distant giants. We looked for patterns, for anomalies, for any sign that the universe might be more than just rocks and stars. Through all of this, one theme stood out: diversity. No two Tellurian planets are the same. Even Earth and Venus, similar in size and composition, have followed vastly different paths. Mars and Mercury, once active, now frozen and quiet. Exoplanets, many of them larger than Earth, and orbiting stars unlike our Sun, expand the range of possibilities even further. Some may be lava worlds, others water worlds, and some perhaps surprisingly Earth-like, waiting in the shadows of their stars. And within that diversity, we found connection. Despite their differences, all rocky planets follow the same physical laws. Gravity, heat, chemistry, and radiation shape them all. What we learn from one planet informs our understanding of others. Mars teaches us about ancient climates. Venus warns us about runaway greenhouse effects. The Moon preserves the early history of impacts. And Earth is our living laboratory, the only example of a world teeming with life. This final reflection invites us to consider our own place. Earth is a Tellurian planet, a rocky sphere in orbit around a medium-sized star in a modest galaxy. Yet on this rock, life emerged. It persisted. It evolved. And eventually, it began to ask questions about the stars, the planets, and the nature of existence itself. We are part of Earth's story, not separate from it. Our atmosphere, our water, our bodies, all are part of the same cycles that shape Tellurian worlds. We are not simply observers of planets. We are planetary beings born of geology and chemistry, living within an atmosphere, drinking water from ancient aquifers, and breathing gases shaped by eons of biology. As we continue to explore, we carry that connection with us. Every spacecraft that lands on Mars, every telescope pointed at a distant star, every spectrograph reading the faint signs of a distant planet's atmosphere, it all begins here, on this Tellurian world, with us. So as you drift off to sleep, imagine yourself floating above a rocky planet. Maybe it's Mars, with its frozen valleys and ancient volcanoes. Maybe it's an exoplanet orbiting a red dwarf, its skies coloured in strange hues. Or maybe it's Earth, glowing softly beneath a veil of clouds, alive with movement, sound, and breath. Let that image hold you. Let the weight of stone and starlight lull you into peace. Because whether we are dreaming or awake, whether we are standing on solid ground or looking up into the sky, we are always connected to the story of Tellurian planets. Good night.